is she? Okay. There is an announcement, and since somebody's here, I'll make it here, but I'll try to remind others as they come in. I can't remember. It seems like I asked last time. Are you taking any other classes here at Lawson, or is this the only one?
It's just speech and this one Tuesday.
What's that?
Thursday. It's just speech and this one Tuesdays and Thursday.
Oh, and they're both Tuesday, Thursday. Okay, well, you know there's no classes on Thursday. Okay, but if anyone else is taking a Monday, Wednesday class, they came out yesterday, even though the governor had stated it back in 12th of June or something like that, that Friday was to be considered part of the 4th of July weekend, so it was going to be a state holiday as well. Well, I had heard last Thursday, I think I told you all this, that classes may be canceled after 12 o'clock tomorrow, okay? But I just heard the rumor. I hadn't seen anything official. So Monday came around, still hadn't seen anything official. So I taught my Monday morning class. It went 8:30 to 11:25. It's a long class. And 11:25, I had 5 minutes between classes. I ran down the hall to check with the other instructors to see if they had come out with any news. They hadn't even heard there was a possibility. I said, well, now this is what I heard on Birmingham campus last Thursday. Oh, we hadn't heard anything about it. So they started looking into it. So I went to my office and I called my boss, the associate dean, got his voicemail, so that wasn't any good. I only had 5 minutes. I needed an answer. I called his secretary, who I heard it from last Thursday, went straight to her voicemail. So I then called the dean, and it went to her voicemail. And then I called the executive vice president, and her secretary picked up, and I gave the situation. They said, oh, we never know until the day of. They don't tell us until the day of that you're getting off at noon. They don't tell us ahead of time. I went, well, what do I tell students? Okay, it's bad enough to do that to employees, but what do you tell students? I mean, if we're not having class next Wednesday afternoon, they don't need to drive all the way out here. Oh, you know. So I called the vice president's office, and his secretary picked up, and I explained the situation to her. She said, we still haven't made a decision yet. I said, well, I'm meeting with a class. In fact, I should already be in the class, and I need to tell them whether they have class on Wednesday or not. I mean, I'm going to be here. I'll be glad to teach it, but if school's going to be canceled, there's no reason for that. Oh, you know, as if, oh, students, they would need to know this by Monday, you know. So she said, well, I'll give you a call. I said, well, as soon as I hang up, I'm going back to class. I won't hear the phone ring. Well, I'll send you an email. Well, I thought, I'm not going to see that either. But she said, I'll have somebody get the word to you. I said, thank you. So I went on to teach my class, and about sometime close to 1 o'clock, one of the instructors I had asked down the hall, she came up, handed me the email. At 12:45 on Monday, they came out. Due to the fact that Governor Ivey is recognizing July 5th as part of the July 4th holiday, the college will close on Wednesday, July 3rd at 12 o'clock noon. So if you know of anyone who's in class after 12 o'clock noon tomorrow, their classes are canceled. This means the blah, blah, this goes into how we'll account for our hours, and that's already taken care of. All classes beginning after 12 p.m. on Wednesday, and all Saturday classes will be canceled. In the summertime, we don't have any Saturday classes. So what is, I mean, he's the vice president for instruction, and he doesn't even know that. We'll resume classes, regular classes on Monday, July 8th at their normal times. Now, you're not in any of the Alabama A&M classes, are you? Okay, because they have some classes on the campus. They haven't decided what they're going to do. So, happy 4th of July. Okay. So, anyway, there's that. I'll try to tell the others in a shorter version when they come in. Any questions on anything we've covered so far? Okay. Well, then we'll pick up from the current slide. And we're starting 12.3 tonight. And some of this, well, I thought we were starting from current slide. There we go. And let me get my pen set up. Okay, here we go. 12.2 is properties of solids. 12.3, properties of liquids. And as noted previously, a liquid is a substance, has a definite volume, but it takes the shape of its container. The reason for that is liquids have a definite volume because the molecules stay close together. They have that good tight proximity to one another, but they're not in a fixed crystal lattice, so they take whatever shape they're in. They're free to move around and take the shape of the container. The molecules move in a flowing motion, yet are so close together it is difficult to compress a liquid. Most liquids share the following common properties. Now remember, in solids, these properties went on and on and on. Liquids are a bit shorter. First, we'll talk about two that we talked about before, cohesion and adhesion. Same definition as before, but now with liquids in mind. Cohesion, the force of attraction between like molecules okay? Now, I realize when we're doing the solids, most of my examples were liquids, okay, because they're so much easier to see and tell in the liquid. But, for instance, water coheres very, very well. It also adheres, okay, but it coheres. The water molecules stick together really, really tightly. They should be, the water should be a gas. Anything with that light of molecular mass ought to be a gas, except they cohere together really, really strongly. Force of attraction between like molecules. That's a pretty ugly K, isn't it? That didn't, there we go. Have you ever jumped into a swimming pool but went flat on your belly? Whoa, that hurts, doesn't it? That's because the water molecules are slow to part, okay? It's called a belly flop. It's called a red belly, okay? Because it hurts, okay? Now, adhesion, on the other hand, is the force of attraction between unlike molecules, okay? Now, the example they give, which is a pretty good one, causes molasses to stick to your fingers. Because that molasses, it likes to stick to just about anything, okay? The force of attraction between unlike molecules. In the case of water, its adhesive forces are greater than its cohesive forces most of the time, okay? It adheres to things very strongly, and for some of the same reasons that it coheres, okay, is because of that hydrogen bonding, and that can happen between like molecules or unlike molecules, okay? So put a glass in water, pull it out, some of the water remains on the glass. Or on your finger if you dip your finger into the water. Not as much as molasses, but still a lot. Now, in the case of mercury, the opposite is true. Mercury's cohesive forces, boy, mercury molecules, they really hang together tightly. And they don't want to touch anything else. So when you see mercury, I hope you never see mercury spilled because it's a toxic material, but if you ever do, it beads up. It tries, all those molecules try not to touch the table. So only the ones on the very bottom actually touch. The rest of them beat up and get like little ball bearings. They look like they're ball bearings until you touch them and they're liquid, but they don't spread, like a liquid. Okay. If you were to put a glass into mercury, pull it out, not a bit of mercury sticks to the glass. Water it would, mercury it wouldn't. Liquid whose adhesive forces are greater than cohesive forces tends to wet any surface it comes in contact, and a liquid whose cohesive forces are greater than the adhesive forces tend to leave objects dry and not wet when the surface happens. Now, the next characteristic or property of liquids is surface tension. And this has something to do with adhesion. And this is really the better example of the belly flop. The reason that hurts so much is because the water molecules sticking together on the surface. Now, I mean, sort of picture this. Here's a water molecule in the middle of water. It sticks to all the molecules around it, okay? Just really hanging on pretty tight. But when you get on the surface, half of those water molecules are gone. So now they hang together to those on the surface even tighter because they're trying to grasp. They don't have anything above them to hang on to, so they hang on to those even tighter. That's what makes water have a large surface tension, okay? Now, I don't know if you've ever seen this before, but if you had a container of water, and there's a picture of it in your book on page 326, and they don't have this on the slide set, I'm pretty sure. If you're very careful when you do it, you can take a needle and very softly lower it into a glass of water. Now, get this. A needle is made out of steel, iron. It's dense. You can very carefully lay it on the top of a thing of water as long as you lay it flat, and it will sit on the water. It will not go down because the surface tension of the water holds it up, even though the steel is denser than water. Okay? And Haley's here. All right. I'll probably announce this to everybody who comes in as they come in. Have you got any other classes this term here at Lawson?
Yeah.
You do? Monday, Wednesday, or Tuesday, Thursday?
Tuesday, Thursday.
Okay. Well, you know Thursday classes are canceled because of 4th of July. But if you know of anyone who has Monday, Wednesday afternoon classes, they've also canceled classes afternoon tomorrow. Morning classes are still on. Afternoon classes and evening classes are canceled. The governor made July 5th, Friday, part of the holiday for state employees, and we're state employees. But we're not coming to work on Friday because we're doing 4 10-hour days. So therefore, a 5-day-a-week employee would be putting in only three days this week. That would be 3 times 8 is 24 hours. Since we're doing 4 10-hour days, our 24 hours would be 10 hours yesterday, 10 hours today, and then only 4 hours on Wednesday, tomorrow. So school will be canceled after noon tomorrow. Okay. So if you know of anyone who's in that. Now, are you taking any of the Alabama A&M classes that are here on Birmingham campus? Okay. If you know of anyone who is, I don't know what they're doing. You'll have to find out from A&M. So, but anyway, for us, class is canceled tomorrow. So that's what surface tension is, the ability of a liquid to hang on to the molecules on the surface even tighter than they hang on to them underneath, okay? And that creates a surface tension. Now, what does soap do? General question, what does soap do? Okay. You know how it cleans? It makes water wet better. That sounds bizarre, doesn't it? But I was just describing, if you had a container of water and you very carefully lowered a needle onto it, flat, that needle will float on the water, even though the needle is made out of iron, steel, and it should sink. It'll sit on the water because of surface tension. But if you were to drop one little drop of detergent, soap, into that water, the needle falls. And here's why. Because the water breaks the surface tension of the water. The detergent breaks the soap breaks the surface tension of the water. It makes the water connect to other things better than it connects to itself. And you know what a soap is technically called? A surfactant. meaning it breaks the surface tension. So that's what all a soap does. It really, in a sense, doesn't clean. It just makes water wet better, so water washes off the dirt, debris, or whatever better. Especially something like an oil or a grease, because water and grease don't get along. Water and oil don't mix, okay? But a surfactant will make them mix better. So that's really what a soap does. It makes it wet better, okay? Now, also in your book, and I should have mentioned this too, mercury, if you put a drop on the surface, it beads up and tries to stay in a little sphere. Any kind of drop in space is going to be a little sphere trying to cohere to its own molecules. But if it's in the presence of gravity, then the bottom molecules get pulled down and the top makes that teardrop shape, the falling raindrop shape. So that's why raindrops look like they do. All right, the next property of a liquid is viscosity. Oh, taking my pen and writing on the screen. That's not good. Is viscosity. Okay. Viscosity is the internal friction of a fluid. Now, time out just a moment here. The term fluid, that pertains to liquids and gases, okay? When you talk about fluid flow, gases use the same properties as liquids do. They have different characteristics, of course, but they have the same properties. So a fluid is either a liquid or a gas. But it's the internal friction of a fluid caused by molecular attraction caused by molecular attraction, which makes it resist a tendency to flow. That's the key. Okay, let's go back to our molasses. Have you ever put molasses in the refrigerator and then pulled it out and tried to pour a cup of molasses? That stuff goes, it may finally get to the edge of the cup and maybe go into it, but it's a slow process. It resists the tendency to flow. Even though you're holding it upside down, it resists the tendency to flow. The internal friction is holding those molecules closely together. So again, this is related to cohesion, okay? Now, how do you make it flow better? Heat it up. And when you heat it up, it'll flow much better, because now the molecules are not as tightly connected to each other, so they do flow a little bit easier. Now, we don't really worry about this a lot in the South, most of the time. But up north, those folks have to change the oil in their vehicles at least twice a year. I'm talking about tractors, big trucks, other things that may not put that many miles on them, but they've got to, because their oils will get so coagulated in the wintertime, when the temperatures are so cold, they don't coat the surface like they're supposed to, and they can burn up an engine. So they have to put a low viscosity oil in their engines in the wintertime and a high viscosity oil in the summertime. And the reason for that, in the summertime, when it's nice and hot outside, the oil gets so thin, it doesn't lubricate well. In the wintertime, it's so thick, it doesn't cover the surface as well. So they have to change the oils. Now, a lot of oils these days, you'll see, and by the way, you measure that in what they call SAE. I don't really know what that stands for, but if you go to the auto parts store or something like that, and go back and look at the oils, you'll see SAE 30, SAE 20, SAE 40, you'll have these different grades of oil. That's related to the viscosity of the oil. So what a lot of oil companies have done, they make blended oils. For instance, 10W40. 10, viscosity of 10, very low viscosity, and also 10W30 or 40, which is higher, so it has some of both. So in the summertime, it coats well enough, lubricates well enough, but in the wintertime, it coats well enough. So that's viscosity, okay? And let me get Brianna here. Okay, now I'm afraid this is indicating that Sharon must be having some more sciatica problems, because she usually is here. Usually she's here before I am, and she usually gets the cord before I get here. Okay. Now, since Brianna came in, let me also announce this. I think I asked this last time. Do you have any other classes besides this one?
Speech class.
Speech class? And is that
It's canceled already.
Monday, Wednesday, or Tuesday, Thursday?
Not Wednesday.
Wednesday.
I read the email.
Okay, all right, you
School
did.
email.
Okay, good. Yeah. Just want to make sure you didn't show up for
Oh, no, I'm not.
okay for class tomorrow afternoon, because after 12 o'clock, no
Yeah,
more
no
classes
more
tomorrow.
classes. Yes.
Yeah, and of course none on
It's
Thursday.
bold and yellow on the computer.
Oh, okay, good. Okay.
That's the test.
Okay, thank you. Not everybody reads their email, so
Oh,
I want to make sure.
Teachers send emails too.
Oh, she did. Okay, good. Good. You got a good teacher. This one probably wouldn't have. Okay. I'll try to tell you in class, but you know, sometimes don't get around to it there. Now, you can't relate viscosity to density. Okay. Within the same liquid, it sort of relates, okay, but not directly. For instance, and they show the picture in the book, a cold oil is going to drop out really slowly, pour really slowly, and spread really slowly. But hot oil comes flowing out, and it just spreads like crazy, okay? And that's because the molecules are moving more rapidly, which does decrease their density. But that's not the only thing. Oil is oil. It's usually higher viscosity than water, but oil is less dense than water. So you can't go by density. Okay. Now, the next characteristic of a liquid is capillary action. Okay. Any of you know what a capillary is?
Is that like a vein?
Okay, veins and any tubular structure can act like a capillary, and does in many ways. In fact, where all the action goes on is in the capillaries. These veins and arteries, the big arteries and stuff, the ones you feel for your pulse and stuff like that, there's no exchange of oxygen or nutrients or anything else with those. Those are big, thick, walled, heavy-duty pipelines, and that's all they are. Where the action's happening is in the very tiny little capillaries that are in near the muscles and your fingers and your toes, everywhere. Those are where the action goes on. That's where oxygen gets exchanged, that's where nutrients get exchanged, that's where liquids get exchanged, that's where wastewater gets exchanged. All the stuff goes on the capillary level. So what capillary action is the behavior of liquids that causes a liquid level. I don't really care for this definition. That causes a liquid level in a small tube which is a capillary, to rise. Okay. Now, are all of you in the medical field somehow already? What, nurses or nurses assistants? Huh? Nurses aid?
Ultrasound.
I'm sorry?
Ultrasound tech.
Oh, I know that's what you're going for. You're already in that?
No.
No, that's what you're going for. But are any of you in medical field right now?
I've done it in the past.
You have? Okay. Have you ever dealt with, especially a diabetic patient or anyone, to get just draw a little bit of blood that you prick their finger?
They let the LPNs and the nurses do it.
Have you seen them do it?
Yes.
Okay. And they get that little bitty tube and hold up near that drop of blood, and that blood just rushes right up the tube. You don't have to suck it up. It just goes up the tube, right? That's capillary action. Okay? Because and again, this goes back to adhesion. Okay? The attraction of unlike molecules. The blood sees the glass or the plastic or whatever the tube is made of, and it is attracted to it, and because the wall of the glass is so small, the hole is so small, it just sucks the blood right up into the tube. Okay? That's capillary action. That's why all the action goes on in your capillaries. Exchange of nutrient, exchange of water, exchange of waste materials, exchange of oxygen, everything goes on in the capillaries because those tubes are so small in your body and have such thin walls, the materials can pass back and forth. Okay? Now, the smaller the diameter tube, the higher the water goes or the liquid goes. The larger the tube, the less high it goes. Okay? If it's adhesive, okay? If the force of attraction is between unlike molecules. Now what I'm going to do here is get away from this slide. Is that okay? Everybody got this one? You do? Okay. And go to our PowerPoints from the book, which are pathetic. I mean, yeah. And they're not all not on there. In your book, if you got your book, you'll see some at the top of the page in different sized capillary tubes and different levels of water going up those, colored water. But at the bottom part of page 327, you'll see this slide. Okay? Now, this shows the difference between strong adhesion and strong cohesion. Water adheres more strongly than it coheres. Okay? So if you have three sized capillary tubes in the sucked down in water, water will rise in all three tubes, but it will rise farthest in the smallest tube. And the reason for that, you see the attraction of the water to the edge of the tube. There's, in a big tube, there's a lot of edge and a lot of water that's not touching the edge. So just the water on the edge gets pulled up a little bit, and it pulls a few of the other water molecules up with it too. Get a smaller tube, now more of the water molecules are in touch with the tube, and they get pulled higher. And then get a tiny little tube, and boy, look at that. It goes way up. That's capillary action. Now, kind of the reverse of this is true if you're trying to take water out of a tube, okay? Because that glass or plastic or whatever the tube is made of, and even this, now look at this. Even on the sides of the tube, the water climbs because of adhesion, the attraction between unlike molecules. Even on the sides of the container, the water climbs. Now that's until you get to fill the container, and if you will, go home and do this, okay? This will be the surface tension part. If you put more and more water in this container until you get up to the level of the top, and then put a little bit more, as long as you put it real slowly and carefully, it won't spill. Keep adding a little bit more water, a little bit more water, a little bit more water, and what you'll see is the water forms a convex layer on it because the surface tension is hanging onto those water molecules, not letting them fall. You can actually overfill a glass of water. Try it. Now do it with water, don't do it with something else, and do it in a sink or something so you don't make a mess, but keep filling the glass and keep filling the glass and keep filling the glass, and you'll see by the time it stops, you'll have a level of water above the rim of the glass. That's surface tension. Before then, it climbs the edge because of adhesion. Okay. Now, what I was going to say, the reverse of this, have you ever gone to McDonald's or one of these other places and gotten a hot cup of coffee in the morning? And you get one of those little stirring sticks, and when the coffee's real hot, you sort of suck through that little stick, but it goes through real, say again?
I said sip because it's hot.
Yes, and you sip it really carefully. Huh?
But it do go through the straw.
It will go through that tiny, tiny, tiny little straw.
Right.
Okay? Well, go and get a milkshake and try to drink that through that little tiny straw. You'll pop your eardrums trying to suck that thing out. Yeah, because the capillary tube hangs on to that, you know. So the reverse is also true. Okay. Now,
milkshake is thicker than that coffee.
Absolutely. The viscosity is greater. Okay. Now, if you put water in a test tube here, it's hard to see here, but this is called, the surface of the water is called a meniscus. M-E-N-I-S-C-U-S. That's down here, but it climbs the edges. Now, of course, there's an edge near you, and it's climbing that as well, but you can see through that and see that the meniscus is down there. But do that with mercury, because mercury coheres more than it adheres, and mercury doesn't want to touch that. It has to touch it down here, but it doesn't want to touch it there. So its meniscus is a raised meniscus, a convex meniscus. This is a concave, sort of like the mouth of a cave. Okay? And if you place these glass tubes, just like those, down in mercury, it actually depresses because it doesn't want to touch the edge of the tube, and it actually goes down more in the smaller tube than it does in the larger because it's trying to get away from those edges. Because water has strong adhesion, mercury has strong cohesion. Okay, so that's capillary action between two different materials. Mercury surface is convex, water surface concave. Water climbs the tubes, mercury goes down the tubes. Okay. And there they give you meniscus. So I will, the water surface is called, let me get my pen back. Water surface is called the meniscus. M-E-N-I-S-C-U-S. Meniscus. Okay. So experimentally, scientists have found that liquids rise in capillary tubes, they tend to wet. Depressed in tubes, they tend not to wet. Elevation or depression in the tube is inversely proportional to the diameter of the tube. So the bigger the tube, they either go up or down just a little bit. The smaller the tube, they rise or they sink more. Okay? And the elevation or depression decreases as the temperature increases, and that's because the added energy of heat makes the water molecules separate more and get they don't hang together as much. It cuts down on the cohesion. And there's a physics connection in your book on oil viscosity. I was just talking about that, and they talk about the Society of Automotive Engineers. That's what SAE stands for. And the W, they use it to call it weight, but it really doesn't have to do with weight, but that's what it's called, SAE 10W40 or 10W30. Okay, 5W20, so on. It's an interesting read, but don't worry about it for the course. That's it for 12.3. No questions, no problems in 12.3. Okay? Let's move to 12.4. There is absolutely no PowerPoint for 12.4. In fact, 12.4 is a tiny little paragraph. So tiny little section, just a few, 4 paragraphs maybe. Okay, so let's go to, no, that's not where we want to go. That's not where we want to go either. Okay, what we want to do is this, okay. Go back to this slide and current slide and properties of gases. Probably I should have put the title on the other one, but I forgot to. That was properties of liquid. This is properties of gases. Okay. Now, I'm going to put the first one down here and do a little bit of explaining. First is expansion. Okay? Now, I'll give the definition. Property of a gas in which the rapid movement of the molecules causes the gas to occupy a bigger volume. Now that's not quite always true, but I'll explain what I mean. But before I do, a little bit of time out here. All matter, when you heat it up, okay, when you heat it up, it does expand a little bit. Solids expand a little bit, not a lot, but a little. Liquids expand a little bit, not a lot, but a little. Gases expand big time, okay? So that's why we talk about expansion as a property of gas, which we don't really mention that much in solids and liquids. They do expand, but not nearly to the degree that gases do. Now, this is talking about whether you have heat or not, but it's just how rapid the movement is to fill the volume, okay? Now, if I were to, remember my supposition, if I were to open a bottle of ammonia and then leave the room and say, I've got to go down to the office for a minute, y'all just sit here and study carefully. After a while, you're going to say, man, what did he do? You know, because that ammonia is going to be burning your eyes, right? If I had put that over a Bunsen burner and turned on the flame and got out of there in a big hurry, it doesn't take any time at all for that ammonia to fill the room, okay? Because the molecules are moving that much faster. So expansion is the property of a gas in which the rapid movement of the molecules causes the gas to occupy a bigger volume. You add more heat, it wants to take an even larger volume, okay? Now, that's expansion. Here's another one, diffusion. Okay? The process by which molecules of a gas, I'll come back and give a caveat here too, mix with a molecule of a solid, liquid, or another gas. Now I'm going to give a little bit fuller definition for that. Okay? And here's the caveat first. Even solids, their molecules will diffuse, but it's a very incredibly slow process. If you wrap two metals together very closely, you will actually get some mixing of the molecules. Some, not very much. And certainly liquids are the same way. If you put two liquids close to each other without a boundary in between, the liquids are going to diffuse. They will mix, okay? Gases do it really easily because the gas molecules are just free to go anywhere they want to. Now here's a little bit better definition of diffusion, or at least an attempt at it. Diffusion is the process by which molecules move from areas of high concentration to areas of low concentration. Okay? So in other words, you open that bottle of ammonia. That bottle of ammonia has lots and lots and lots of ammonia molecules in it, right? You open the bottle and now the room has almost no molecules of ammonia. So those molecules of ammonia try to go from the high concentration in the bottle to the room where there's low concentration. That's what diffusion is. It's following a concentration gradient is what they call it. Now, the illustration of that is a pretty poor one, but I like it because I like to garden.
That's another word,
Diffusion? The word after that?
No.
Process. Oh.
No, I'm saying it's another word that I know is math, but in science, what is that word? Osmosis over here.
Ah, you're very good. Okay. Osmosis is the process. That's an excellent, excellent example. Osmosis is when it goes from a high concentration, for instance, in your cells. Okay. Your cells, as they're doing work and stuff like this, they get waste products. So when they come in contact with the capillary of, say, your blood vessel, then by osmosis, the waste product moves out of the high concentration of your cell into the low concentration of the blood vessel, and the blood takes it away, gets it to the kidney, and then reverses the process, and by osmosis again, it goes out. Almost always by a process of diffusion. Now, one thing that helps that osmosis is what they call a semi-permeable membrane. And that's what your kidneys have. The kidneys have semi-permeable membrane that lets the waste product goes out of the blood vacuoles into the kidney, but doesn't let it go backward out of the kidney into the blood vessel. So that's why the kidneys tend to do it. And I don't know this for a fact, but I bet you the liver does the same thing. The liver pulls out the contaminants, the toxins and things like this, and doesn't let them go back into the bloodstream. Thank you, semi-permeable membrane. But yeah, you're absolutely right. Osmosis is another process. It's a little more active of a process than diffusion. But here's a dumb example I was going to give. Like I said, I like to garden, and I found that if I have a garden, whether it's vegetable garden or plants, flowers or things like this, and I try to keep blueberries or whatever, and I try to put it out there, the Bermuda grass diffuses out of the yard into the garden, okay? You can see those Bermuda grass things just take off and go, and they go right toward from areas of high concentration to areas of low concentration. I pull all of them out there. Next time I go back, they've come again. They're always diffusing from areas of high concentration to low concentration. That's diffusion. Gases do it big time. Okay? Now, and I said this earlier, and I'll say it just one more time. Well, I'll say it many times. What a fluid is is a substance, okay, either a gas or a liquid. In other words, it's a material that takes the shape of the container. Liquid take the shape of the container, gases take the shape of the container. So a fluid, it can be either a liquid or a gas. So when I doubt if you'll get into it, but fluid mechanics, that's the mechanics of liquids, but also the mechanics of gas flow, both of those. And that's it for 12.4. Boy, we're moving today, aren't we? So let's now move to 12.5. This one, you're going to have some examples, okay? So I think I'll go to a new slide. Does everybody have this one so far? Okay. So let's go to a new slide, and let's do density. Now, density is a property of all matter. Solids, liquids, and gases, okay? It's a property of all matter. Now, there's two types of density, and this book uses a slightly different notation than some books, but I'll use the one this book does. Sometimes I'll slip and do back. dm, that's a D with a subscript M, is a mass density. Okay? And how it's defined, dm is the mass per unit volume. Now, volume is a capital V. Little v was velocity, capital V is volume. Mass is a little m. Okay? But there's another kind of density, weight density. Okay? And weight density is then defined to be the weight. And remember, weight is a force, so this book calls it F sub W, which most books don't, but I like that notation. It reminds you it is per unit volume. Now, why do you reckon we have two different kinds of densities? Mostly because we have two systems of measurement. Remember, in the SI system, they focus largely on mass. So in the SI system, we're going to use mass densities most of the time. Maybe not all the time, but most of the time. But the good old U.S. customary system that they used to call the British system, or the English system, we don't even have a good unit for mass. There is one called the slug, but no one uses it. So they have to use, or tend to use, weight density. So many pounds per cubic feet, rather than grams or kilograms per cubic meter, okay? So that's why we have the two different types of density, because we have two different systems of measure. This is used mostly in the SI system, and this is mostly in the U.S. customary, okay? You can do them both in metric and U.S. system, but mass density is usually in, and by the way, the units in the SI system, kilogram per cubic meter. I said it, but I didn't write it down. And most of the time in the U.S. system is pounds per cubic foot. Okay? Those are the common units. However, density is one thing that uses that. I don't know if you remember the book talked about CGS. It tends to use that more because you can use grams per cubic centimeter. Okay? Just because a cubic meter is a huge volume. A huge volume. Okay? I think I've told you before if you picture this door right here, I'm going to pull it too. Hopefully it won't be locking Sharon out if she gets here. Well, I doubt if she will. But I'm not going to stay until I do pull it too. Okay, a meter is about the height of that doorknob, right? And that width of the door is just about a meter too. And if you came out here about that distance as well, that's a cubic meter. So that wide, that high, and that deep. If you imagine that filled with water, you know what you got? A ton of water. I mean, not just figuratively, you've got a ton of water. Very close to 2,000 pounds of water if you had a tank that was that size. 1 meter high, 1 meter wide, and 1 meter deep. What's that?
Fish tank.
Yeah, well, that's a pretty big fish tank. If you go to someplace like
an aquarium.
Yeah, like an aquarium. Yeah, you're absolutely right. Some of the Chinese restaurants will sometimes have those great big old fish tanks. That'll be close to that much. Even those are less than a cubic meter. That's a ton of water, literally. In fact, a little bit more than a ton of water. Okay? So that's why quite often we'll refer to density in grams per cubic centimeter, because a cubic centimeter would be like your little fingernail by your little fingernail by your little fingernail. That would be like one of those tiny little sugar cubes, right? That don't sweeten anything. That would be a cubic centimeter, and 1 gram or grams per cubic centimeter. That's an easy thing to measure. Kilograms per cubic meter, that's a huge thing to measure. So water, for instance, is 1,000, and they put a bar over that second zero. I don't think they should. I think this is exact. 1,000, this is water. The density, the mass density of water is 1,000 kilograms per cubic meter. That is a little bit more than a ton of water per unit per cubic meter. That's a huge density, I mean a huge number, okay? Because a cubic meter of water has a mass of 1,000 kilograms, which is about 2,200 pounds, which is more than a ton. The density of water, however, because a cubic foot, that's much less. A cubic foot is about this deep, that wide, that long, okay? That's a nice box, okay? And that's only going to be the weight density of water would be 62.4, I believe it is what they give, 62.4 pounds per cubic foot. See, a cubic foot is a lot smaller than a cubic meter. It takes probably 30 cubic feet to make 1 cubic meter, okay? That's a lot of cubic feet, okay? So that's a much more reasonable number. 1,000 is a lot of kilograms per cubic meter. That would be just for water. In nearly all forms of matter, density usually decreases with temperature. As temperature increases as temperature decreases. Why? Because when you increase the temperature, the molecules move faster, they bounce harder against each other, and they tend to spread out, so your density decreases. When they cool, they tend to get closer together, so your volume decreases, but you have the same mass, so your density increases. Now, there's one notable substance that is a big exception to that, and it's only there for a very small temperature range, but that is good old water. What happens to water when it freezes? It expands. Everything else, just about every other substance on the planet, when it freezes, it gets smaller. Water gets bigger. That's why if you have a very hard, cold freeze, we haven't had one, we had a few years ago, there was that Arctic vortex that came through that really dropped the temperatures way, way, way down, we actually had some pipes burst. You have to worry about that. Up north, they really worry about it because they have that all the time. But down here, we usually don't have that cold of temperatures to make pipes burst, but it can happen. Okay? So you think that's a bad thing for ice to expand when it freezes? Actually, all life depends on that. Because if you think about the ponds, the lakes, even rivers, way up north, if ice sunk when it melted, when it froze, in other words, got more dense like most materials do, if that happened to ice, then it would freeze from the bottom up, and it would kill most of the organisms living in that stream or lake or pond. But because ice floats, it becomes less dense, it goes to the surface, and therefore there's always liquid water underneath, so animals can still live in there. Awfully cold, but they can still live. Okay? Thank you, ice, for that strange characteristic. Okay. Now, here we go back to our other slide. And this is where we left off last time. All right. Here's a table of common densities of various materials. Now, you don't need to know these, but just to get the idea. Now, again, I don't like mass density in kilograms per cubic meter because the numbers are so stinking big. I prefer grams per cubic centimeter, which are very reasonable numbers. But aluminum, 2,700 kilograms per cubic meter, because a cubic meter is just such a big quantity. Brass, 8,700. Concrete, 2,300. Copper, 88.9. Cork, very light, floats, 240. Ice, 917. Notice that's less dense than water. Water is 1,000. Ice is 917. Now that is ice around 0 degrees ice. Once you get a lot colder, it starts shrinking again, but still it'll float. Okay, iron, 7,800. Lead, this. Look over here at the weight density. The numbers are much more reasonable. 169. Yeah, they're still big numbers, but they're very reasonable numbers. Those are just way too big. So, to make the conversion to grams per cubic centimeter, you just move the decimal over 3 places. 2.7, 8.7. That's why I like grams per cubic centimeter. They're very manageable numbers. Okay. Lead, very dense. So these are some of the common solids, ice being solid water. Liquids, notice alcohol less dense than water, gasoline even less dense than alcohol. Mercury, though, look at mercury. Look at its density. Huge, enormous. Even lead floats in mercury because it's less dense than mercury. Okay? Oil, less dense than water, a little more dense than gasoline and alcohol, but less dense than water. Seawater, a little denser than water. This is fresh water, pure water, 1,000, which would be 1 gram per cubic centimeter. Okay? 62.4 pounds per cubic foot. Seawater, 64.0 pounds per cubic foot. Now, the ramification of that, have any of you ever been swimming in the ocean or the Gulf of Mexico? Yay or nay? Okay. If you've ever been swimming either in the Gulf or the ocean. Okay?
The beach?
Yeah, at the beach, exactly.
Just left Gulf Shores.
Second, yeah, at Gulf Shores. Okay? Did you notice it's easier to float?
It is.
It is, because salt water, seawater, is denser than fresh water. So it's easier to float. If you really want to float...
No, I don't know how to swim, so I didn't go too far. I rode the waves, but
right.
I didn't go too far.
Right. But go to Salt Lake City. And the Great Salt Lake, that's even saltier than seawater.
Oh, yeah, that was so salty.
And
let me tell you what water is very salty. Orange Beach.
Really?
Oh my goodness.
Okay.
It was either Orange Beach or Pensacola.
Right.
Oh my goodness.
Yeah.
It ain't no water you want to get in your mouth.
I don't know. I don't think, I know I've never been there. I doubt if I ever get there. But if you ever go to the Dead Sea over in the Holy Land, you know, near Israel and stuff, that is so dense. You can't sink. I mean, you bob up like a cork, you know, because the density is so great. Okay, let's go to the gases. Now, the gases you have to say what temperature and what pressure, because gases vary a lot. If you change the temperature, they get less dense. If you increase temperature, they get less dense. If you decrease pressure, they get less dense. Air is about 1.29 kilograms per cubic meter. So you see, those are good units for air, okay, or gases. Ammonia, 0.760. Carbon dioxide, 1.960. Carbon monoxide, 1.25. Helium, really light, 0.178. Hydrogen, the lightest gas there is, 0.0899 kilograms per cubic meter. Nitrogen, 1.25. See, that's a little bit less dense than air, not much. Oxygen, a little bit denser than air, 1.43. Because, see, most air is approximately 80%, this is approximately 80% nitrogen and 20% oxygen. So, therefore, it's in between the two, but closer to nitrogen. Propane, a little denser than air. Okay. So, you don't need to know those, but this is a table you can go and get your densities. Okay. Now, whoa, that's the last slide in the chapter. But that doesn't mean we're that close to the end of the chapter. We just don't, yeah, we're pretty close. So let's go back to our other slide then and do some of these examples. They saved them all till the end here. Well, we had a few earlier. Find the weight density of a block of wood that's, let me get my pen back. Okay. A block of wood that's 3.00 inches by 4.00 inches by 5.00 inches. So it's going to be 3 inches by 4 inches by 5 inches. I don't draw blocks very well, okay? So this is 5.00 inches. Obviously, mine's not to scale. Okay? Find the weight density of that block of wood if it has a weight of F sub W, that's the weight, 0.700 pounds. Okay. Now, we have a little problem here, don't we, Houston? Okay? And that problem is our units. They're not consistent. Okay? Because our density in our tables is pounds per cubic foot. These are pounds per cubic inch. I mean, this is pounds in cubic inches. So we're going to have to do a conversion here. Okay? So, let's first figure out the volume. Okay, what is density? That's what we're looking for. The weight density, that's D sub W. What is that? Weight density. Okay, weight is the top part. That's, I'm sorry, I was going to put W sub F, and it's F sub W. Okay, the force due to weight, F sub W, which is exactly that, divided by volume. They didn't give us the volume. What is our volume? How do you determine the volume of a rectangular parallelepiped? That's what you call that. Anyone know? What volume is of a rectangular solid like that? Length times width times height. And right now I'm calling this the height, I'm calling this the width, I'm calling this the length. You can name them anything you want to, but that's it. So what is the volume?
Times
5.00 inches by 4.00 inches by times 3.00 inches. Okay, and that's going to be 20 times 3 is 60.0, 3 significant digits, cubic inches. You multiply the units as well as the numbers, right? Got it? But we don't want it in cubic inches, I don't think. I think they want it in cubic feet. So what we have to do is do a unit conversion. Blank blank is equal to blank cubic feet. Okay? Now my first blank there in my conversion factor is for numbers. Don't worry about the numbers yet. The second blank is for units. Always put the units in their place. Now which unit do you think is going to go where? Inches or feet? Top or bottom in that second blank of the conversion factor? Which is going to go where?
inches on top.
No, if inches were on top, then you have inches times inches, not cubic feet. So no, you want the inches to go away, so you put them on the bottom. Since the inches were on top here, put them on the bottom here. And put feet on top, because that's where feet is here. It's in the numerator. Okay, now, before you do anything else, match the numbers with the units. How many feet are in an inch, or how many inches in a foot?
Inches in a foot. There's 12 inches in a foot.
12 inches is 1 foot. So that indicates you're, okay, except we're not dealing with inches and feet, we're dealing with cubic inches and cubic feet. So you got to cube this, cube that, cube that. I can do all three of those real easily. This one is a little bit harder, cubing 12, because 12 by 12 is 144, and then multiply it by 12 again, and you get a pretty big number. So do 60 divided by 12 cubed, and see what you get. A pretty small number. 60 divided by 12 cubed.
0.035.
0.035, is that what you said?
Yeah.
Give me one more digit.
Okay, then it would be 347.
347, and you rounded that? Okay. That sounds reasonable. Okay? So now we can put it in our formula. It's 0.700 pounds per 0.0347 cubic feet. And do that division, and what do you get? Looks like something greater than 20. Is it?
How many do you want me to go through?
One more digit.
20.2.
0.2?
Yeah.
And that would be pounds per cubic foot, which is exactly what we measure density in. And that's what the book got to. Now, they did theirs a little bit differently, but it's okay. Now, if you might wonder, where they come up with that number, if you got your book and looking at it, of no, I see, they did the same thing we did. Okay. They flipped it around and did a different thing, but, you know, got the same answer. Okay. Now, how are we doing on time? All right, got about 15, 20 minutes, okay? Or we can still go into 7. No, I think it's still 6:30. Okay, sorry. I knew y'all would be excited to hear that. Okay. Let's do example 2. Anyone need example 1 any longer? Got it? Okay. The book does it slightly differently, but they get the same answer. You can do it their way if you prefer to mine. Okay. Example 2. Find the mass density. So this time we're looking for mass density. And what is mass density? What's its definition? Mass density? It's mass per unit volume. Okay. So mass density of a ball bearing with a mass of, so the mass of the ball bearing is 22.0 grams, and I would just as soon leave it in that. And the radius, because it's a ball, that's a little sphere. So the radius of that sphere is 0.875 centimeters. Okay. Now, I see mass. I can fill that in, but I don't see a volume there. Does anyone know what the volume of a sphere is? A ball. Volume of a ball. Okay, I don't see it in the front of the book. Let's see if it's in the back of the book. Ah, yes it is. If you got a book, the back inside cover of the book, okay, there is the formula for a sphere. What is it? Especially when you know the radius of the sphere. Back inside cover. Very, very back. Very, 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 very back. Very bottom. Volume of the sphere. 4/3 pi r cubed. You're not used to that symbol pi? Get used to it. Okay? The volume of a sphere is 4/3 pi times the radius cubed. Okay? Now I'm going to do this in terms of my favorite units, grams per cubic centimeter. But then the book is going to want us to do it in kilograms per cubic meter. Okay? So this is going to be 4/3 times pi times 0.875 centimeters cubed. Now, most of your calculators, I bet, have a pi key on it somewhere. Okay, if you don't have one with it, you can use 3.1416. But if you got a pi key, it's a lot easier to just press that key once rather than type all those digits in there. So 4 divided by 3 times pi times 0.875, and then find the, usually it's a caret key. So this would be, I'm going to show you how to punch this in. That would be 4 divided by 3 times pi times, and you don't have to do parentheses, but 6.875, and then look for a key that looks like that, a little house top, and then put your 3 and then press equal. Now if you don't have that key, look for a key that's something like this: A to the B, B to the A, X to the Y, or Y to the X. It'll be one of those 4 keys. You hit that one rather than the caret key. And then type in 3, then press equal. What you get is an answer. Anybody? In my mind, it's going to be something, when you do 0.8, or let's just call it 0.9 times 0.9 would be 0.81 times another 0.9 would be a 0.72. So let's just call it 0.7 times 4. That would be about 2.8, somewhere in that area. Is that what you get? 2.81, and the units are cubic centimeters. You cube this unit just like you cube the number. Okay? So now we can go up and plug it into our density formula. The mass was 0.87. Oops. You're letting me make a mistake here. I almost hit a really bad mistake there. Okay. That's going to be 22.0 grams divided by 2.81 cubic centimeters, and that's going to be something on the order of 8 or 9, maybe 7 or 8, I'd say. 7 point what? 7.83, and that would be grams per cubic centimeter. Now, since the book wants it in terms of kilograms per cubic meter, I think I told you this before, all you do is move the decimal 3 places to the right. So that would be 7,830 approximately kilogram per cubic meter. Okay? Now, if you go back and look at your table of densities and look at that, you'll see that's awfully close to iron. So this was probably a steel ball bearing, which is a good guess because that's the most common metal on the surface of the earth is steel. So we got 7,830 kilogram per cubic meter, or 7.83 grams per cubic centimeter. Good deal. You see how to do that? All right. Now, let Brianna get caught up a little bit. Is this making sense? Okay, everybody got it? All right, let's go to example 3. Can I erase? Yay? Okay. Find the weight density of a gallon of water weighing 8.34 pounds. So we got 1 gallon of water, and it's a weight density of a gallon of water weighing, I'll say F sub W, that's the weight of the water, is 8.34 pounds. Okay? And asking for weight density. So this is D sub W. Now what's the formula or definition for weight density? Okay, don't look it up. What is the formula for it? No, weight divided by volume. That's not a velocity, that's a volume. Weight divided by volume. But wait a minute, we got the weight, 8.34, We don't have the volume, we have the capacity. 1 gallon. Okay? Now, the book will come up with a number, and they tell you, but let me tell you, in case the book doesn't give you that, go to the back of your book, not quite as far back as your answers are, but back there in Appendix C, which is your tables. Remember, I've taken you here before. Conversion tables. There's weights and measures there. Table 1, we don't need that. Conversion for length. Table 2, we don't need that. Conversion table for area, we don't need that. Conversion table for volume. Table 4, that looks like it might be it. Now, if you'll see 1 U.S. fluid gallon is 4 U.S. fluid quarts, 8 U.S. pints, 128 U.S. fluid ounces, or 231 cubic inches, or 0.134 cubic feet. That's what we need. 1 gallon is 1.134 cubic feet. And I think that's what you see. No, they use cubic inches. Strange, strange, strange. I wouldn't use cubic inches. I would use 0.134 cubic feet, because that's what you're going to want to get. So 1 gallon of water from your table is 0.134 cubic feet. Okay? So, let's put the weight, 8.34 pounds, divided by 0.134 cubic feet. And what does that give you? $62.2. That would be pounds per cubic foot. Okay? Now we were given in the text, it was around 62.4 pounds per cubic feet. So if I were looking at these, I'd say either we have a little bit of a round-off error, or maybe this water is heated a little bit, so it's a little less dense than the water they gave in the book. Let's see what they give as the answer. They said 62.4. Okay? That is totally bizarre. Okay? And you know why they got that? They went the cubic inch route and then converted cubic inch to cubic feet, and they came out. This is close enough for government work. Don't feel bad if you are off just a little bit. If you're really close to the answer, be satisfied. Okay? Think we got time to do one more example? All right, let's do it. Probably have room on this slide, but can I erase? Okay. Let's do example 4. Find the weight density of a can of oil, 1 quart, weighing 1.90 pounds. So here we're looking for weight density, which would be D sub W. And how is that defined?
Force of weight over volume.
Yeah, the force unit weight, or the weight divided by the volume. Okay? Now, this time they said of a can of oil, and they tell you of a quart of oil, weighing 1.90 pounds, with F sub W 1.90 pounds. When they say weight, weighing, that's the weight. Okay? Now, what we've got to do now, that's a capacity of oil. I would go back to my table again. What was it? Table 4, wasn't it? Conversion table. And let's see if they tell us what a quart is. Boo hiss. They don't. Okay. Now what I would do, folks, because 4 quarts makes a gallon, I would take that 0.134 cubic feet, divide it by 4. Okay? So this will be 0.134 cubic feet divided by 4, because this is per gallon, that's gallons per quart. Okay? That's going to give you the number of cubic feet in a quart. So take your weight, which is 1.90 pounds, and divide it by 0.134 cubic feet. Now let me show you a little trick. Since you're dividing by something that's already a fractional form, just multiply the numerator by that 4. Okay? Rather than dividing the denominator, multiply the numerator. And let's see what you get. 4 times 1.90, I think is going to be 7.6, no, yeah, 7.6, yeah, 7.6 pounds, I believe, divided by 0.134 cubic feet. And see what you get. Now you could leave that in the denominator over 4, that works too, but it's just a little easier doing it this way. 7.6 divided by 0.134. Anybody?
56.
Say 56? Is that what I heard? 56.9 pounds per cubic foot. Okay? How did it compare with the book? 56.9 pounds per cubic. Did you just look at the book or did you actually do the math?
No, I did not.
All right, good. I'm just kidding. Okay. Perfect. Way to go. Okay, now, does that make sense? Yeah, water was 62.4 pounds per cubic feet. Oil is less dense than water, 56.9. Seems reasonable. If you go back to your table, oil was listed there as 54.2. So this is just a little bit denser oil. It's just a can of oil. And maybe they got the can in on it too, so that may be why it's a little denser. I don't know. All right. You think we're going to have time for another? I think not. Right? Okay. We'll start next time with example 5. But the good news is, look at this. We got enough done here that you can do some homework exercises. Okay? And I think you can do some of the odds 1 through, say, 19 in problem set 12.5. And we are awfully close to finishing the chapter. Now here's the question for you then. Do you want me to go on and run off the test so you can work on it on this long weekend?
Yes.
Okay. Will any of you see or communicate with Sharon?
You stay like 3 hours away.
Oh yeah, that's what I thought. Probably not. But it's not going to bother because it's not going to be due any sooner. Make sure I get the right test. All right, let me start over. There's test 1, or chapter 8. There's chapter, whatever the next, no, 5, then 8. Here is chapter 12. Okay. I'm going to need to go run off the test because I only brought my master. I didn't think we'd get this far tonight. So I'm going to go on and stop the recording.